Assalamualaikum and good day everyone. So for this video, we'll be doing the chapter summary for chapter 9, that is Kinetic Theory of Gases and Thermodynamics. So for this chapter, you'll have 5 subtopics that are Kinetic Theory of Gases, Molecular Kinetic Theory and Internal Energy, First Law of Thermodynamics, Thermodynamic Process, and Thermodynamic Work. So we start with the first subtopic. In the first subtopic, we have the kinetic theory of gases, and also we have a few assumptions that will be showing us that the gas are perfect gas. Then you'll have the equation for the root mean square speed of the gas molecules. VRMS is basically this kind of the average speed of the gas molecules, okay, that are in a container. So we have so many gas molecules inside, and each of these gas molecules is having its own speed. So to get a kind of average reading, then we'll find VRMS. So we have 3 kT over m. K here is the Boltzmann constant, m is the mass of the gas molecules, or you can also use this equation that contains R, molar gas constant, and also m, big M, that is the molar mass. So all the units for all the quantities must be in SI unit. And also for the subtopic, you have ideal gas equation. I believe you have learned this from your secondary school. So we have PV equal to NKT or PV is equal to nRT. So P here is the pressure, V is the volume, T is the temperature. Everything as always must be in SI unit when you do your calculation. Then you will also have the relationship or the equation for the number of moles, small n. Small n is actually equal to mass of gas divided by the molar mass, and it is also equal to the number of gas molecules and the number of Avogadro number of gas molecules in 1 mole of gas. So from here you can see a relationship between the mass and also the number of particles. And apart from that, you'll also have gas pressure, the equation for the gas pressure. We're talking about the gas pressure in a container. It's not the gas pressure or the air pressure outside. Okay, so the equation can be expressed is either in terms of density. Okay, it's 1 over 3 rho VRMS squared, or you can also express, or you can also relate with this equation, that is PV equal to 1/3 number of molecule, mass, and VRMS squared. Okay, then we have 9.2 is molecular kinetic energy and internal energy. For the kinetic energy, okay, you must know the difference between the equation for translational kinetic energy for a molecule, or we call it as average translational kinetic energy. It's 3 over 2 kT. And if the question asks us to find the total kinetic energy, so we have to multiply this term with the total number of gas molecules. Then you'll have this equation. Total translational kinetic energy is 3 over 2 nKT. And you know that nk can be also expressed as small nr, is 3 over 2 nRT. So you have 2 choices of using the equation for total translational kinetic energy. So for your information, for kinetic energy, you have few types of kinetic energy. Is translational, and you may also have the rotational, translational, and rotational. So for rotational kinetic energy, it will be different for depending on the type of molecules we're talking about. So in this case, we can see that the monoatomic molecule, gas molecule, will have 0 number for the degree of freedom. For diatomic gas molecule, will be having 2 rotational, 2 possible way how it can be rotated, and polyatomic gas is 3. We have to look at the number of translational. Okay, the degree of freedom for translational, so we have 3 for all type of gases. So we have 3 for monoatomic gas, 3 for diatomic, and also 3 for polyatomic gas. We total up 2 numbers of degree of freedom. Hence, we'll have 3 for monoatomic gas, 5, and 6. 5 for diatomic and 6 is for polyatomic. So this is the number of degree of freedom which we will use this number when we find the internal energy. Internal energy is basically the summation of kinetic energy and also the intermolecular potential energy, but the potential energy is ignored, okay, because of the intermolecular forces is negligible between the gas. So our internal energy is basically equal to the kinetic energy, but it depends on the number of degree of freedom. It's not exactly the same here because here is the total kinetic energy, but here is only for translational kinetic energy. So you have U is F/2 nRT, or you can also express this equation in terms of number of gas molecules. So it's F/2 nKT. So this is basically based on the principle of equipartition of energy. That is, for every degree of freedom, it will contribute KT/2 for every number of degree of freedom. The next subtopic is subtopic 9.3, that is first law of thermodynamics. For the first law of thermodynamics, we have this equation is delta U equal to Q minus W. Delta U is the change in internal energy, Q is the heat transferred, W is the work done. So for each of this quantity, we have delta U, Q, and W. We have to know exactly the sign convention for these quantities so that we can include it in the equation when we do our calculation. So for your information, we have Q positive means the heat flow into the system. So system here means our system of gas. So we assume our gas is in a container. It can be in any shape of the container. This is just my drawing. So if Q negative, it will be heat flow out of the system. And we also have the sign convention for the work done. The work done positive means that the work is done by the system. So the gas molecules is doing work. So when the gas molecules is doing work, meaning that it will relate with the volume. So it will be expansion of the container. And then if the work done is negative, it means that the work done on the system. So the work done is on the system by the surrounding. Okay, so you have to know all the sign convention. This is really important when we calculate or when we apply the first law of thermodynamics. And another quantity here is delta U. Remember, delta U is the equation for U is F/2 nRT. So if you have delta U, meaning that is F/2 nRT final minus F/2 nRT initial. Delta U here is depending on the temperature. It means that if your temperature of the gas of the system is increasing, delta U will be positive. And if your temperature is decreasing, your delta U will be negative. The sign convention plus minus really matters for the first law of thermodynamics. The work is done by the system. So the gas molecules is doing work. So when the gas molecules is doing work, meaning that it will relate with the volume. So it will be expansion of the container. And then if the work done is negative, it means that the work done on the system. So the work done is on the system by the surrounding. And another quantity here is delta U. Remember, delta U is the equation for U is F/2 nRT. So if you have delta U, meaning that is F/2 nRT final minus F/2 nRT initial. Delta U here is depending on the temperature. It means that if your temperature of the gas of the system is increasing, delta U will be positive. And if your temperature is decreasing, your delta U will be negative. So the sign convention plus minus really matters for the first law of thermodynamics. For the subtopic of 9.4, it is thermodynamic process. So we have 4 processes that are started with isothermal. Isothermal is for constant temperature. Okay, we have isochoric or isovolumetric. It is for constant volume. And isobaric is for constant pressure. and also adiabatic. For adiabatic, pressure, volume, temperature is not constant, but what is important here for adiabatic is your Q will be 0. There will be no heat flows in or out of the system. We always relate our case or our process with the ideal gas equation. So we have PV equal to nRT. So PV over T is always constant. If you have few conditions, P1 V1 over T1 will be equal to P2 V2 over T2, and you can always compare with a few conditions for your question. Okay, for isothermal, we have constant temperature, meaning that we'll be having the equation that will relate pressure and volume. Okay, PV here is PV equal to P1 V1 is equal to P2 V2. Okay, that's the first thing. And the second thing is you have to always relate with the first law of thermodynamics. So we have learned just now that Q is equal to delta U plus W. Okay, since our T is constant, there will be no changes in temperature. Hence, delta U is equal to 0. Hence, our first law of thermodynamics will be Q is equal to W. Okay, so this is for isothermal. For isochoric or for isovolumetric, we'll have V constant. P1 over T1 is equal to P2 over T2. Okay, that is for the ideal gas equation. For the first law of thermodynamics, okay, you have constant volume. Okay, so the equation will be Q is equal to delta U plus W. So when the volume constant, there will be no expansion or compression. So there will be no changes in the volume. Okay, it means that there will be no work done for the case of isovolumetric or isochoric. So delta V is equal to 0. Because you have to always remember work done is related to the volume. So if there is a changes in volume, meaning that the work done on the system or by the system. But if there is no changes in volume, there will be no expansion, no compression. It means that no work done on the system or by the system. So in this case, your first law of thermodynamics becomes Q is equal to delta U. Next, for isobaric, so we'll have V1 over T1 equal to V2 over T2. And for first law of thermodynamics, Q is equal to delta U plus work done. Because P is constant, so all the quantities in the equation is maintained. And for adiabatic process, okay, we'll have P1 V1 over T1 equal to P2 V2 over T2. For the first law of thermodynamics, so when Q is equal to 0, it means that delta U is equal to negative work done. The last one is for thermodynamic process is that you have to be able to draw or to sketch the graph of P pressure against V for thermodynamic process. So for every temperature or for isothermal, your graph must be a curve. Okay, this is isothermal process. So if you have two curves in a graph, it will be two temperatures related. For every curve, it is representing one temperature, T1, and here is T2. So for thermodynamic process, for isothermal, it will be like this. If the system is expanding, it will be directed to the right. Or if the case is compressing, so the volume will be decreasing, so the arrow will be to the left. Okay, it depends on your case. Then you have the graph of isochoric. Isochoric is constant volume, so it must be like this. Okay, so this is isochoric, is either up or down. Isobaric is constant pressure, so this is the graph of isobaric. If it is expanding, it will be directed to the right or vice versa. Then another case is adiabatic. We change all the values. P changes, V changes, T changes. So the graph will be coming from one curve to another curve, meaning that the temperature is changing. So this is the graph of adiabatic. Okay, so the graph of adiabatic will be steeper compared to the graph of isothermal. Okay, now it comes to the last subtopic of this last chapter of this semester, that is thermodynamic work. So for your information, we have the equation for the work done for the isothermal process, isobaric, and also isochoric. Okay, so this is the equation for isothermal process. The temperature is constant, so you can express your equation in terms of pressure, P1 over P2, or in terms of volume, V2 over V1, ln V2 over ln V1. And this is the equation for the isobaric process, so P V2 minus V1. And last one, there will be no work done for isochoric process, so it's equal to 0. As I explained just now, that if you have change in volume is equal to 0, there'll be no work done. Okay, so the work done is equal to 0. So that's all for the chapter summary for this semester. I hope it is helpful for you to do the revision, to answer the PSPM questions, and good luck. Thank you.